Hello everyone and welcome to lecture today. So recall that in the last lecture we introduced the concept of limit, continuity, and derivative of a parametric curve in 3D. The derivative was defined in a very similar way to how the derivative of a single variable function is defined using the limit definition, and essentially ended up being exactly the same thing as what you would expect. Right? If you have a parametric curve r of t, which is some function f of t, g of t, and h of t, the derivative of this parametric curve ended up being expressible as a new vector, which is just the derivative of each one of the components. This is also sometimes called the velocity vector, but if the parameter t is not time, it doesn't necessarily equate to an actual physical velocity. This only happens if t is the time parameter. So the nice idea here is that we also were able to define a unit tangent vector, which is the vector that points in the same direction as v, but has unit length. This is always going to be the vector r prime of t over the length of r prime of t. And the last thing we really talked about was the idea of arc length in 3D. Where we have this very nice formula that is s of t, the arc length at some value of the parameter t will always be the integral from, say, some like t naught on the curve up to t of the magnitude of r prime of tau, the magnitude of this derivative, d tau. The integral of this gives you the relationship between arc length along the curve and any value of the parameter t on the curve. It's important to note that this works when the magnitude of r prime is positive everywhere. And we can also say that the derivative of arc length will always be equal to the magnitude of the velocity vector at any parameter value t, the magnitude of this first derivative at any parameter t. So this is something that we saw in the last lecture that'll be very, very convenient to use in this lecture. This is also sometimes called s prime of t when we move back to the prime notation from single variable calculus. And this is also why we can say that this unit tangent vector is also the same thing as r prime of t over ds dt, or r prime of t over s prime of t. So these ideas, the unit tangent vector, the arc length, and the fact that the derivative of arc length with respect to the parameter t is the magnitude of velocity, will be very, very helpful for us a little bit later on in the lecture when we talk about acceleration. But this is just kind of a summary of some of the topics that we talked about in the last lecture. And now what I want to do is go over many various properties that the derivative of parametric curves has, because these properties are going to be super important in knowing how to deal with differentiation of a parametric curve is going to be super important going forward. So in the following, we're going to assume that r of t is our parametric curve. C is a constant vector. We're going to take the function w of t to be some general function of t. And we'll also take some other d of t to be a different parametric curve. So a vector function of t. So these properties come and are relatively easy to verify using the standard derivative rules. The first one is going to be the constant rule, or the derivative of a constant will always be equal to 0, the 0 vector. This is because the derivative of c1 will be 0, the derivative of c2 will be 0, and the derivative of c3 will be 0. This is a relatively straightforward one to consider. The second one that we have is what's called the constant scalar multiple derivative rule, which is similar to what you might expect. If gamma is a constant, I need gamma is a constant is here as well. So if gamma is a constant, we have to expect that the derivative of the parametric curve gamma times r of t is equal to r prime of t All of these are relatively easy to go through and verify. A couple of them are a little bit longer, but I recommend you going through and doing it by hand just to get some practice. The next main property is that the derivative of w of t times r of t obeys the product rule in the sense that this is going to be the scalar function w prime, so the derivative of w times r of t plus w of t times r prime of t. This is the scalar multiple product rule. Next one is going to be the sum difference rule. So if you have the derivative of r of t plus or minus d of t, this is going to be equal to r prime of t plus or minus d prime of t. Next one is, I think, being a pretty interesting one. The product rule for the dot product and for the cross product still holds. And this definitely requires some investigation here. R of t dot d of t will always be equal to r prime of t dot d of t plus r of t dot d prime of t. Or this is the vector dot product between parametric curves. I call this the dot product rule because it's the product rule, but for the dot product. This one was the sum difference rule. just like we have the product rule for the dot product, the derivative of the parametric curve, r of t cross product d of t also holds. This will be r prime of t cross d of t plus the vector r of t cross d prime of t. This is what I call a cross product rule. The last one that's going to be really important for us a little bit later on is the idea of the chain rule. And this is the scalar chain rule, it's sometimes called. If you're taking the t derivative of r of w of t. So r is a parametric curve that depends on some w, which then in turn depends on some t. This is the same thing as r prime of w of t. So the derivative of the parametric curve with respect to w times w prime of t. And for shorthand, this is sometimes just called dr dw times dw dt. This is the scalar function chain rule for composition of a parametric curve with scalar functions. But so these rules are all relatively straightforward to show. It kind of just involves taking one of these rules and going through the component definition for each one of these. I'll prove 5 right here just to show you what I'm talking about, but I recommend going through and showing each one of these. So r of t dot d of t is going to be, well, if r of t is f of t, g of t, h of t, and d of t is d1 of t, d2 of t, d3 of t, then r of t dot product with d of t is going to be equal to f of t times d1 of t plus g of t times d2 of t plus h of t times d3 of t. Taking the derivative of this, is going to be the same thing as taking the derivative of this entire expression right here and the derivative of a sum becomes the derivative of each of the individual terms in the sum, and you can do the product rule on each one of these individual terms to get df dt times d1 or f prime plus f of t times d1 prime of t. Same thing for this term, and same thing for this term right here. We can do the product rule on this, on this, and on this, which when we kind of regroup things is going to end up giving us r prime of t dot product with d plus r of t dot product with d prime of t. So this shows that, right, this property holds. All of these are really the same. You can do this for each one of these properties, and I recommend you going through and doing that just to make sure that you're kind of comfortable with what it is you're doing. But these properties are going to be super useful for us, and specifically what I want to start doing is getting into the next main geometric vector that's going to be really important to us. And this is the idea of the normal vector. We've been able to define the tangent vector before. Right now what I want to do is define the normal vector. And in order to do that properly, what I want to first do is introduce the idea of curvature of a curve in 3D. This is a concept that we can actually exactly write down mathematically very, very nicely. So what I've done here is drawn down the same picture from the last lecture, which is our curve R of t. That's our curve C right here. And the derivative of R of t, which is the tangent vector to the curve, and also the unit tangent vector, which has unit length and is tangent to the curve with length 1. Right, so R prime of t is always going to be changing depending on the velocity at a given point. But t hat is always has unit length. The magnitude doesn't change at all. Which is why t hat, in some sense, is the perfect measure of the curvature at a given point. Right? Our intuition for curvature should be the following. For two different curves, say this curve right here and this curve right here, I think it should be clear that this curve right here should have a very high curvature relative to this curve right here. It should have a low curvature. We're thinking of curvature as the general curviness of the curve. So if you think of how the tangent vector, the unit tangent vector t hat, is acting on this curve right here, t hat goes like this, and then changes to this, then changes to this, and then changes to this right here. Whereas on this curve, as we traverse the curve, it goes from this to this, to this, to this. So it's a much more gradual change to t hat on this curve than it is on this curve. And this is the sole reason why we're going to define curvature the way that we are. So this is kind of like an informal diagram that you can use to think about curvature. But it really is intuitive, and it helps you kind of figure out exactly what is meant when we define curvature as the following function. We say that the curvature kappa at a particular point of arc length is exactly equal to the magnitude of the rate of change of the unit tangent vector with respect to arc length s. I'm choosing to use arc length here for my derivative specifically because this is something that's common to all parameterizations of all curves. No matter what parameterization you choose, you can always parameterize the curves via arc length. So it makes a lot more sense to use this instead of a general parameter. It's also much nicer. This formula is much nicer. However, you do have to be careful, as we'll see, when converting from the curvature in terms of arc length to curvature as a function of t. So this is the definition of curvature, that we define it as at any given point of arc length, the rate of change of the unit tangent vector at that point. And it's the total length of this vector. So it's a number. Right? This is the length or the magnitude of the derivative of the unit tangent vector with respect to arc length, or the change in this vector t hat along the curve. to obtain the curvature as a function of t, where t is any arbitrary parameter of the curve, we can do just this by doing a chain rule here. Right? The curvature is the same thing as a function of, say, s of t. And we know then that this is the magnitude of dt ds, which by the chain rule is the same thing as dt hat dt times dt ds. And remember that as long as the magnitude of velocity vector is positive, we can express the arc length s as a function of t with any parameter t, and vice versa, we can express t as some function, t of s. This is kind of neat because it also means that from the implicit function theorem, dt ds is going to be the same thing as 1 over s prime of t. Informally speaking, you can think of this as saying it's 1 over ds dt, but really this is a very, very nice property that comes directly from the implicit function theorem. From Calculus 1. It's a super useful theorem and is essentially used to calculate complicated derivatives, but in this context we know that ds dt is just the magnitude of the velocity vector. So this curvature then, when I plug in dt over ds, is 1 over the absolute value of v of t. This is the same thing then as the magnitude of the derivative of t hat with respect to the arbitrary parameter t divided by the magnitude of v of t. So this is the curvature as a function of some arbitrary parameter t. You see that the formula is a little bit more complicated than the formula for arc length, which is why whenever possible we want to use the arc length formula for curvature. It kind of gets rid of this velocity division. But either of these two formulas work out, and they're both equivalent to one another, as I've just shown here from the chain rule. So the idea here is going to be the following. What we're going to do is use this curvature expression to get a very, very nice result that you might have seen in a physics course, but if you haven't, that's okay. If this is the first time that you're seeing it, it's perfectly fine. And essentially what this is going to be is a decomposition of the acceleration vector in 3D into two separate directions. The first is the tangential direction to the curve, and the second is the normal direction to the curve. So in order to do this, we first need to define and understand what the normal direction to the curve is. Specifically, why it's normal. So this gives us another really big definition here. The unit normal vector to a curve we call this n hat, just like t hat we call the unit tangent vector. The unit normal vector is defined as the unit vector in the direction of the derivative of the unit tangent vector with respect to arc length, the rate of change of this vector with respect to arc length. Specifically, we say that n hat will be equal to the derivative of t hat with respect to arc length over the length of dt hat with respect to arc length. Equivalently, this is the same thing as the rate of change of t hat with respect to arc length over the curvature as a function of s. Which is the same thing as saying that the rate of change of the curvature, or the tangent vector, the unit tangent vector with respect to arc length, is going to be the curvature function as a function of x, which is just the magnitude of this vector times this new unit vector n hat. So this is the definition of the unit normal vector, and I want to prove to you that this actually is a normal vector to the curve, or perpendicular to the tangent vector of the curve, just to kind of justify why I'm calling this thing the unit normal vector. So why is this normal or perpendicular to any curve? Well, take the definition, or one of the defining properties of the unit tangent vector. The dot product of the unit tangent vector with itself has to be equal to 1. We take the derivative of both sides of this expression, because both of these depend on the parameterization of the curve. I'm going to do this with respect to arc length, but you could also do it with respect to parameter t as well. We get dt hat ds dot product t hat plus t hat dot product dt hat ds on the left hand side from the product rule for the dot product has to be equal to 0, which gives us that 2 t hat dot dt hat ds has to be equal to 0, because the dot product order doesn't matter, it's commutative. And if t hat dot product with dt hat ds equals 0, then the angle theta between these two vectors must be equal to pi over 2, or 90 degrees. So t hat must be perpendicular to dt hat ds. And therefore, dt hat ds is normal to the curve, or points in the normal direction. Now, it's not necessarily unit length, because this magnitude is not necessarily 1, which means that to get the unit vector in this direction, we have to divide by its magnitude, or the curvature of the curve at every point at s. But this is what gives us that t hat is perpendicular to dt hat ds. And at this point, we have everything that we need to do a thorough investigation of the acceleration vector. First, what I want to do is just show you what this unit normal vector looks like on a general curve, so you can get some sort of a feel for what it is this vector is saying. So recall the example that I was talking about in the previous lecture, which is the cardioid, in 2D, if you look at the 2D cross-section, but actually has a z component that kind of goes up and down as this sine of 3t here. And I want to exactly show you what the unit normal vector is. In this case, the unit normal vector is the vector that's pointing in the direction of dt hat ds over the magnitude of dt hat ds. And this is always going to be perpendicular to the vector t hat. If we kind of watch this as the curve goes around, you see that at every single point on this curve, this unit normal vector is pointing in a specific direction. What's called the unit normal vector, it's always perpendicular to t hat right here. So this is very neat. And now that we've seen this, we can go through and directly investigate what the acceleration vector looks like for any given curve. Specifically, we define the acceleration vector as the second derivative of the parametric curve with respect to the parameter. In physics, this is typically called a of t, but really this is just the second derivative of the position vector. Equivalently, we can think of this as the first derivative of the velocity vector, r prime of t, and we know that the velocity vector is the same thing as the magnitude of the velocity vector times the unit tangent vector along the curve. Equivalently, you could write this as s prime of t, the derivative of arc length with respect to t, times the unit tangent vector. So either of these two interpretations or ways of writing this down works, because remember that the velocity vector r prime of t, or the first derivative of the parametric curve, is going to be the same thing as the magnitude of r prime times the unit tangent vector. And this magnitude of r prime is the same thing as the derivative of arc length along the curve. So I'm going to use this format right here just because it kind of cuts down on the number of things that I have to write down when I'm differentiating this. But using the product rule, we have that the second derivative of the position vector with respect to time, the acceleration vector, is going to be exactly the derivative of this, so the second derivative of arc length with respect to the parameter t times t hat plus s prime of t, which is this, times the derivative of the unit tangent vector with respect to the parameter t. This is just normal scalar multiplication, and this is the product rule property 3, the scalar multiplication product rule. And so this is really doing something very neat for us. And you might not be able to see it right away, but I'm going to try and describe this very succinctly right here. This S double prime is called the tangential acceleration of the curve, because it's the rate of change of arc length with respect to time, or the total amount of local tangential acceleration in the direction t. This is why it's tangential acceleration. For this term, we have to rewrite this a little bit. Recall from the chain rule that dt hat ds, or dt hat dt, is the same thing as ds dt times dt hat ds. So the rate of change of t hat with respect to the parameter t is the same thing as the rate of change of s with respect to t times the rate of change of t hat with respect to arc length s. So dt hat dt is the same thing as s prime of t times dt hat ds is the same thing as the curvature as a function of t times the unit normal vector of the curve. So when I plug this in here to dt at dt, this is the same thing as the curvature at the parameter t times s prime, so s prime of t squared, all times the unit normal vector. And this is called the normal component of acceleration at any time t, or any value of the parameter t. So essentially what we've just shown is that the acceleration vector for any curve is the second derivative of the position vector of points on that curve, and this is exactly equal to the tangential acceleration times the unit tangent vector on the curve plus the normal acceleration times the unit normal vector on the curve, where tangential acceleration is just the second derivative of arc length with respect to t on the curve, or the first derivative of the magnitude of the velocity vector along the curve, and the normal acceleration at all points along the curve is the curvature at any point on the curve times the speed at that point squared, or the curvature at any point times the magnitude of the velocity vector at that point squared. And this is really an incredible result. It's basically saying that the acceleration at any point for any parametric curve is always going to be a decomposition of acceleration tangential to the curve and normal to the curve. Visually speaking, what this means, and I'm just kind of drawing our picture again here, is that the acceleration vector at any given point on the curve is going to be some vector that is pointing in the immediate direction of acceleration, and this can always be decomposed into two separate parts: the part that's moving tangentially to the curve, and the part that's moving normally to the curve, which is very cool. And so just to get a visualization of this, I added on the acceleration vector here, as well as the unit tangent vector, the unit normal vector, and the velocity vector, to give you an idea of how these things are changing as we kind of move around the curve. So you can very clearly see that at every given point, this acceleration vector is kind of pointing in a general direction, and this general direction that it's pointing is a decomposition of a component in the direction tangent to the curve, as well as a component normal to the curve as well. So I think it's really incredible that this concept of three-dimensional motion and velocity and acceleration are all very nicely described mathematically via parametric curves. And what we've done here is construct a portion of what's called the Tnb frame for any curve. So t hat and n hat are two very important directions at any given point on any given curve. To finish this off and really kind of describe motion along a curve at any given point t, we need to introduce one final vector, which is called the binormal vector. And this has the notation capital B hat. And this is the unit vector that is perpendicular to both t hat and n hat at any point on the curve. And there's really no better way of defining this than the cross product. Because we know that the cross product from our cross product properties will give us a vector that's perpendicular to the original two vectors that we were taking the cross product of. So this is perpendicular by definition of the cross product. Not only that, if you look at the length of b hat, this is the same thing as the length of t hat cross n hat, which we know is the magnitude of t hat times the magnitude of n hat times sine of the angle between t hat and n hat, which is pi over 2. The length of t hat is 1, the length of n hat is 1, sine of pi over 2 is 1, which means the length of b hat is 1. So for a given parametric curve, the collection of vectors t hat, n hat, and b hat is called the Tnb frame, also sometimes known as the Frenesara frame, and governs the motion along the curve. And you can do some really neat things with this Tnb frame. Specifically, you can develop what's called the Frenesara Formulas, which is a system of differential equations that essentially gives you this Tnb frame when solved. And the only thing that you need is to know the curvature at every point along the curve and what's called the torsion at every point along the curve. I won't be getting into this in this class, but it's a very, very cool application of calculus and vector calculus to the motion of any curve in three-dimensional space. But to finalize kind of the picture in your mind of this motion, this Tnb frame, this is the velocity vector in purple, the unit tangent vector in orange, the normal vector in red, and the binormal vector lastly now in blue. And I think you can very clearly see that if we let this travel around the curve at every single point on the curve, this Tnb frame is doing exactly what you expect mathematically, and gives us a nice physical description of motion along this curve. It's very cool. And so what I want to do to end the lecture is just revisit one of the examples that I did in the previous lecture, which is the helix, to show you how we can kind of use what we just did to really understand motion along helix. You'll remember in that lecture I showed that the velocity magnitude is always constant for the helix as kind of traverses around. The velocity vector is not constant. It has a changing direction as you move around the helix, which is given by this. But when you get the magnitude of this, it ends up being constant. It just depends on the parameters that define the helix. I showed how to find the unit tangent vector as well. And then lastly, I found the arc length and how that relates to the parameter theta when the helix is parameterized by the angle. So kind of moving forward, using what we know now about acceleration, we know that the tangential acceleration is going to be the derivative and so using what we know that the acceleration or the second derivative of position with respect to the parameter is going to decompose into a tangential component plus a normal component both of which can be relatively easily computed. At of theta is going to be the theta derivative of s prime of theta. S prime of theta is square root of r squared plus b squared. which is constant, the derivative of a constant is 0. So the helix has no tangential component to its second derivative. We can't call this a direct acceleration because theta is the parameter of the curve, and theta is not dependent on time, but you can actually extend this to theta being dependent on time as well using the chain rule. So this is kind of a very neat idea. But the tangential component of the second derivative along this curve is 0. The normal component, however, is going to be the curvature as a function of t times s prime of, oh, not t, but theta. This theta is our parameter, times s prime of theta squared. And so this is going to be kappa of theta times the square root of r squared plus b squared squared. So an of theta is going to be kappa of theta times r squared plus b squared. So now what we need to do is investigate kappa of theta and figure out what the curvature is going to be at every different point along this curve to really get an idea of what this an is going to be. And it turns out this is going to simplify to something very, very nice. And so to solve for a kappa of theta, we need to recognize that this is going to be from our previous formula, the derivative of the unit normal vector with respect to our parameter. This is a vector. It's going to be the magnitude of this divided by the derivative of arc length with respect to our parameter, which is just the velocity or a first derivative magnitude. So recall that for the helix, t hat has the following form. I'm just going to copy this from the previous example. And so the derivative of this vector with respect to theta is just going to be equal to derivative of sine, which is cosine. This is negative r over the square root of r squared plus b squared times cosine theta, be positive r over square root of r squared plus b squared, and the derivative of cosine theta is negative sine of theta. And then lastly, the derivative of this is going to be 0. It's constant. So the magnitude of dt hat d theta is going to be the square root of this squared plus this squared plus this squared, which just ends up being r over the square root of r squared plus b squared. So the curvature at any point on the helix is going to be this over s prime of theta, which is the square root of r squared plus b squared. So this is going to be r over r squared plus b squared. And this is the expression for curvature on the helix. It's constant for any angle theta. Not only that, but if we plug this into our normal acceleration formula, we get that an of theta is going to be r over r squared plus b squared times r squared plus b squared, or just r. So the normal component of acceleration is constant, And the acceleration vector then for our helix is always going to be 0 times d hat plus an of theta, which is r times n hat, which is going to be r times the vector negative cosine theta, negative sine theta, 0. Now keep in mind this is not a true acceleration because we're differentiating with respect to theta here, but it's relatively easy to figure out what the true acceleration is going to be in terms of the chain rule, right? This derivative right here, this a here is the second derivative of displacement with respect to theta. You can figure out how this relates to change in time if theta is changing with respect to time around the helix by just using the chain rule and getting a nice connection here. In fact, I'll do this in a second. I just want to emphasize here that we've solved for the second derivative of the helix, and this is saying that it's r times the vector negative cosine theta, negative sine theta. This is always pointing inwards to the origin. And just to get a nice graphical visualization of this, we're going to look at the helix over one period here from 0 to 2 pi, and if I play this trajectory here, you see very clearly that everything that we've just calculated is completely verified, where the velocity vector has a constant length. The acceleration vector is always the radius times negative cosine theta sine theta, and this stays constant for any point on the helix. Which is really quite incredible, because the AT, tangential acceleration, is 0, and AN is just r times n hat, which is negative cosine theta, negative sine theta. Not only that, but this also gives us some properties of the circle as well, because if we take that b and take the limit as b goes to 0, we end up getting a circle for our curve. So we've just proven a lot of stuff about the circle as well. So specifically, what I want to say here is that the first thing is, if theta, say, depends on time, then all of these calculations can be expanded upon. We know that the A calculated up here is the acceleration in the sense of it's the second derivative with respect to theta. But if you want, say, dr dt, from the chain rule, this is going to be the same thing as dr d theta times d theta dt. So the idea here is that dr d theta is the velocity vector that we calculated up here. By the chain rule, the real true physical velocity is just dr d theta times d theta dt with respect to time. And all of these things can be rewritten in this way using this idea, and you can get some very, very interesting statements of motion, and really all of circular motion in physics when you end up kind of doing angular acceleration and circular motion. It all comes from this idea of parametric curves. So I'm not going to go over this in detail, but just an important thing to note. And the second thing that I wanted to note is that when b goes to 0, we get a circle in the curvature formula. Curvature as a function of theta goes to r over r squared, because b is going to 0. So the curvature becomes 1 over r, which is a classic formula for the curvature of a circle. The curvature of a circle is 1 over its radius. But I think this will conclude the lecture today. Thank you so much for tuning in. I hope you learned something and that you had a fantastic day.